welcome you all to the alumni talk of today's session. I welcome Mr. Abhilash Pandurangan. He is alumni of SRM Institute of Science and Technology. He completed his undergraduate in computer science engineering in the year 2015 to 19 batch. Currently, he is pursuing his MS in data science at University of Southern California, Los Angeles, and he has so many work experience in the internship cadre. Like he worked with Frenzy Labs in Los Angeles and SS Live Bangalore. Also, he has been part of research internship at National University of Singapore. Apart from this, he has done so many projects, namely Apache's path-based collaborative filtering recommendation system and automated disease detection for chest X-rays and so on. He has awarded with the USC Viterbi Masters Leadership Award in the year 2020 and also SRM Performance Based Merit Scholarship Award while he is pursuing his undergraduation at SRM University. Also, he is being the Vice President Finance Viterbi Graduate Students Association at USC currently and volunteered at Ideas Data Science Conference happened in September 2019 at Los Angeles. With this introduction, I just hand over the session to Mr. Abhilash Pandurangan. Welcome, Abhilash. You can start the session. Thank you.
Thank you, Lavanya ma'am. Thank you for the introduction. It's really great to be back to SRM University and giving back to the alumni. So today I'll be talking about machine learning for games. And before that, I would like to thank Dr. Pomal ma'am and also Annapurni ma'am for giving this opportunity. And I'll be starting my presentation now. Yeah, I hope it's visible. So just to give a brief introduction, so I'm currently doing my master's in University of Southern California, as Lavanya mentioned. So I did my bachelor's in computer science at SRM University from 2015-2019 batch. And today I'll be presenting about machine learning for games. Yeah. So before going that, let's understand what is the importance of machine learning in game development. So, we can use machine learning to build agents that can play games as opponents. So basically, it will be a bot which you can play against with, or it could also be playing along with human players as a NPCs, that is non-playing characters. So as you can see over here, this is like one of the old ML agent, AI agent, you can say, wherein it's playing X and O game with a human player, and the machine is able to predict using some rule-based methods and so on. So that is how it started in 1950s when they started to build agents for games such as board games such as X and O and so on. So there are various applications of machine learning and AI in terms of game development. So as I mentioned earlier, like we can have a game agent as an opponent, or you can play alongside with human players. Like for example, if you're playing games like PUBG and Fortnite, wherein you have like multiple players, you can have like a AI agent or a machine learning agent which can play alongside with human players, and that can really help the game to be more interactive and make the game more immersive in nature. And it can also make you can also use machine learning to make the games more beautiful. So you can create a really good environment in games wherein you must have seen that there are some games wherein the game universe is being created. And in those games, you can really use machine learning to generate images, and you can make the game more beautiful so that it's interactive. And you can also make the same nature. You can also make it more realistic interaction. You must have seen some games wherein there are some glitches or some places where it's not really working. So using machine learning can detect those rendering and make sure that it's properly rendered and make sure it's more realistic in nature. And also like add some physics into it. For example, some games they might need that the environment actually follows rules similar to Earth. So, for example, you're having a flight simulator. So for a flight simulator, you need to make sure that it's not going to like go out of this Earth or something like that. So for those realistic interactions, it's really important that you have you use some kind of logic or some kind of AI agent which can actually make sure that all the physics and all the environment concepts are embedded into the agent. And also you can it's really important to make engaging mobile games. So with the advert of having a lot of mobile games like PUBG and Fortnite, we can actually make it more engaging by using all the chat features. So using some machine learning techniques like natural language processing, you can actually understand the sentiment of the users, and you can try to make the game more interactive in nature. So as I was mentioning earlier, you can also use some kind of universe creation on the fly methods. So there are some games wherein the game agent actually, when the game agent actually moves forward, the universe is being created. For example, like Minecraft, it is a very popular game wherein you start building things from scratch. So in those games, it's really important that you create an universe on the fly. So those things can be done through machine learning, wherein you can use something like a generative adversarial network to actually create a set of images on the fly to make it more interactive and engaging. And also, as I mentioned earlier, to model all these complex systems like the physics, it's very important to have some kind of logic which is not just based on rule based, but more on machine learning basis. So as I mentioned earlier, like we can use machine learning and AI in game development. So now that we have learned this, so what is exactly machine learning? So before going into more details, let's learn what exactly is machine learning, and why do we teach machine learning or AI to play games? One thing we can say is like AI, to measure the intelligence capability of AI, we can actually try to first test it on games. Like just imagine you want to test a robot. So before going into the real world, you want to make sure that it is first tested in a game environment wherein the robot can fail, and even if it fails, it's not really going to impact any human or any object. So that's really good measure of AI. So it's considered since 1950s that you can really measure the intelligence capability of AI using games. So that is one reason. And apart from that, it's really convenient for testing and learning. And some early researchers in machine learning like tested on games like chess, backgammon, and Go, wherein all these are like board games, and they tested some AI agents which can play the games. So some early research has been done on this, and games also like help develop AI in other fields. For example, can the AI agents you're developing in games can use it as a test bed for new AI algorithms which you're developing. And so you see, these are some recent research articles that, like for example, this one day ago from DeepMind, which is a Google developed organization, wherein they develop game agents using reinforcement learning. And as you can see over here, they say that they have developed a new toolkit for generating games. So this is some research is ongoing, and this is something that we want to focus on because a lot of companies like Google, Facebook are actually focusing on building AI bots and making sure that games are being generated on the fly. And another side part is like since it's the pandemic and people are actually playing more games, it's really important to make the games more interactive as well. And we can see like it's not just the small board games that AI bots can play, but the AI bots can also play games like Dota 2. Dota 2 is really a complex game, and for such games where you have multiple players, the AI bots are still able to beat the pro players, the pro human players who have been playing the game for many years. And so before going to more concepts, let's just have a quick review of what is machine learning. So machine learning is basically, as the word suggests, it's basically to automatically learn and improve from experience without being explicitly programmed. So what I mean by that? So basically, you don't want to program like if and then rules. Like for example, if I pick this particular object, then you do this or something like that. You don't want that kind of a implicitly programmed wherein you have like a rule-based approach. So you want some kind of algorithm which basically learns from the experience that it gets. So machine learning algorithms can be of three types: supervised, unsupervised, and reinforcement learning. Supervised algorithms are mostly those wherein they are like task driven. That is, they predict the next value or using some previous data that we have. So they require a lot of data that you already have, and using the data, they kind of predict the future values and things like that. So that is a quick, small overview of what is supervised learning. And there's also something called unsupervised learning, wherein you don't have the exact output. So in supervised learning, you have both input and the output you have, and based on that, when new input comes, you try to predict for the exact output that will be there. But for unsupervised, you don't have the output for it. So given an input, you try to have some kind of a clustering technique, and you have, using the data that's with you, you try to identify some kind of a clusters and some kind of unsupervised approach. But here's where I'm going to focus on, and I'll tell you why. This reinforcement learning is, think, is a game changer in terms of AI, building AI agents for games, because it can learn from mistakes. So that's, you don't really need a lot of data. Imagine you're going to program a bot that plays Fortnite, and for Fortnite, you don't want to have like images of all the, maybe all the ammunition, all the guns that's there in Fortnite or something like that. You don't want all that particular approach wherein you collect a lot of data, and using the existing data you start programming the agent. You don't want that kind of approach, but you want to go more into the reinforcement approach, wherein you don't really need too much of data. It generates data based on the needs. Like basically, it creates an environment, and from that environment, you learn from the mistakes that happen, and you'll be going more into that. So let's before going to reinforcement learning, we can see this quote by Alan Turing. He's a really famous computer scientist, and he says that instead of trying to produce a program to simulate the adult mind, why not try to produce one which simulates a child's? So, if this were subjected to an appropriate course of education, one would obtain the adult brain. So, what does this mean? Actually, he's saying that why not, like, instead of saying like, okay, let's make an agent that's going to be exactly like human, why not make like an agent which actually is like behaving like a child? So you must have observed like a child in its like maybe in first 2 years, they how they start to like talk, how they start to like walk. They actually try to like, initially they make some mistakes. Like, for example, like the child might not know that like you should not touch fire, so they might go near the heat, and they might feel some, they might get burned, and then after that they learn that okay, if I touch fire, I'm going to get burned. So they learn from mistakes. So why not take that approach? Why not like build an agent which is like a child? Basically, it will make mistakes. It's fine, but it will learn from the mistakes, and it will use that learning process, and it will be more powerful than building a full-grown robot. Like you're going to build a whole human, you need to make sure you put all the rules like, hey, don't touch fire, and just drink water and things like that. So you don't want that kind of approach. So reinforcement learning comes exactly into that picture. So basically, it's a type of machine learning wherein the agent learns how to behave in an environment by performing actions and observing the results. So basically, the key thing to observe over here is, so basically there's an environment, and you're performing some kind of action, and after performing the action, you're observing the results. For example, as I mentioned earlier, let's take the same case of like touching the fire. So there's an environment wherein you have fire, and the child actually performs an action. The action in this case would be touching the fire, and observing the results would be like to get burned or something. So that's how the reinforcement learning process happens. So basically, you have some set of actions, and you observe the results based on the actions, and you get either you get some kind of learning experience from that. So it's a kind of a approach wherein you're understanding the decision making through experience. So you're learning something from experience, which is more valuable. So it and also one more thing is, we don't exactly have all the data that we need. So only things that we know is whether we succeeded or we failed. That is, for example, in this game you can see over here, this is a popular Atari game. Whereas I guess most of you must have played this game. So basically, you need to make sure that you hit all the blocks, and you make sure you get the highest score over here. And the failure in this case would be that you lose the game. Like this, for example, in this case, it has lost the point. So that would be the reward for it. So reward is something like, if you succeed, you get a positive reward, and if you fail, you get a negative reward. So a negative reward is something like a punishment you can consider. So that's how the reinforcement learning works. Basically, it deals with maximizing reward. So you can generalize that all the reinforcement learning algorithm does is it tries to maximize these rewards. Like you can say this particular game, when the agent is trying to play, and the rewards would be the point score over here. So if the point increases, it knows that it's doing something good. If the point it becomes reduced, it reduces, or the lifeline is hit, then it knows that it's a punishment, and it has to learn from the experience. So just to give you an overview of the entire learning, reinforced learning process. So there is some set of state. For example, you're playing a Mario game. So what you see in the screen is this particular screen that you see. So that is the state, S of T. And you have an environment. So environment is Mario Bros. That's a game which you're playing. And the current status, you're close by to this particular enemy. So that is the current state right now. And what is the action? So action is to move right. So suppose you're selecting the action to be moving right, then the agent gets some reward based on that action. So for each step it takes, it gets some kind of a reward, and that reward is fed back to the agent, and the agent decides, okay, so it makes some mistakes. Suppose the enemy actually kills Mario, then it gets a negative reward. So it's a feedback loop process. So it keeps happening over and over and again. So it's not something that you learn it like one go, like you play one game and the agent is able to learn. It's a iterative process. It means like you need to keep doing and keep failing. So it needs to like after so many iterations, it will be able to understand, like it will be able to maximize the reward for each state. So at this state, it will know that okay, it has to move right, and it has to click that particular question mark to get into a next level, and so on. So this is how the reinforcement learning process works. So the key thing over here is rewards. So it's really important to decide how to assign these rewards. And before going to that, let's understand why reinforcement learning. So there's a lot of buzz of reinforcement learning currently, and you can see that you can understand why it's like that. So games like Atari games are like those old games wherein you can play with slow resolution and so on. And there are like so many games which can be played, all using reinforcement learning. And a good thing over here is there are so many games which has like a driving capabilities, which can be then transferred into like self-driving cars, and those cars, those learning process that been learned from these games can then be later transferred into the real world environment. So and also you can make robots. So all that robots do can be like made into some kind of environment wherein the robot actually learns in that environment rather than learning in real world. So you don't want to have some kind of a robot that fails in the real world. But when it comes to a reinforcement learning agent, it can actually fail. So failing in an environment wouldn't be that costly, and you can really learn from the experience. So that's why it can be applied to real world robots as well. And it has been really successful in beating Go champions. So Go is really complex game. Is for those of you who don't know what exactly a Go game is, it's similar to a chess, but it's more complex. And the whole state space search of Go is really large, and it's difficult to model by like just doing some rule-based algorithms. So like AlphaGo is like an agent uh, uh, which has been done by Google's DeepMind research, wherein they're able to beat the Go champion, and they were able to beat him like 5-1. So reinforcement learning has been proved really successful in the past few years. Uh, Before going to that, like let's understand what is reward function. So I mentioned earlier that reward function is really essential for understanding the reinforcement learning agent. So we can see this game of table tennis. So let's say that there are two agents. We have an agent one and agent two, and both are playing together. And you can see the green symbol over here, which represents the positive reward. But you can see that when the agent actually hits the ball, it gets a positive reward. But when it loses the ball, as you can see over here, when the ball misses the bat, then it gets a negative reward, as you can see over here. So that's how it works. You basically get a positive reward for every good actions that you take, and you get a negative reward for every actions that are costly in nature. And this need not be like we have in this case. I'm telling you that we have two separate agents, but there are some other techniques wherein you have one agent which plays with itself. So there could be some kind of adversarial reinforcement learning agent which can actually like learn from itself by playing like so many times by itself. It can have like it can be like getting both the rewards, like it can understand like okay, so if I make this move, I'm going to get a positive reward. But if I make some other move, I'll get a negative reward. So it will understand the way to maximize the reward, and at the end, the episode reward would be the game score. So at the end, it wants to like win the battle, right? So the reward function designing is really important because that's how the reinforcement learning agent actually learns. So, like as I mentioned earlier, it could be either a negative or a positive. This is something that's the tricky part of reinforcement learning algorithm, because if you have a really good reward function, then you can have really good agent. But if the reward function is not able to learn well, it is not able to maximize the rewards at the end of the each game, then it will be pretty much useless. Um, Okay, now how do we design the reward function? So let's take this particular scenario where I say that your agent is a mouse and your enemy is cat. You don't want to land in the cat place, and the agent doesn't know where the cat is, where the cheese is, or anywhere. So the agent just goes around. It can go anywhere in the step, and basically, if it gets a cheese like this one, it gets a positive reward. Basically, let's say like if it gets this particular cheese, you get a positive like of one point. But if you get this particular bundle of cheese, you get like 1,000 points. So the question would be like, should the agent just go to nearby places, or it can go like all around and explore different places and get a better reward? So that is the one big issue in reinforcement learning, that whether to maximize the reward, like just make it more safe play and just go to nearby cheese and get those maximum cheese which is nearby, or let's go to like let's explore all different places, even though it might go land up in a tile wherein there's a cat. It still is like it's not afraid of going to all the tiles. So you want to make sure that agent is not like, okay, very lazy or greedy approach wherein it just goes to like, okay, nearby cheese and gets those things as a positive reward, but also like tries to go to like places like here wherein it can actually get a better reward. So it's important to understand this difference, and we can understand even better with this particular example. So let's say you have infinitely small amount of cheese. So by going to this, the agent, again the same case over here, but instead of cat we have poison, let's say, and if the agent can go anywhere around this board, and let's say, but this particular cheese is now infinitely small amount of cheese. That means like you can get one cheese, but you need to go at each step you go, you get a negative reward. Like you don't want to get too much of steps, but each step you go, you get like one reward. So let's say the agent starts here and it goes here, it gets like positive reward, and it says, oh, that's really good. So like if I go to this place, I'll get a one cheese. So again, it keeps going over and over. It gets just stuck over here. Or if it goes to this particular cheese, where it gets like 1,000 points, and that's what you want the agent to reach. So this is a classic problem called exploration versus exploitation. So exploration is like a case wherein you want the agent to go all around the state space. That is, you want this agent to make sure that it actually explores all the places before just considering on one thing. And exploitation is in this case where it just keeps going to nearby cheese and gets those reward functions because it's easy to get. So that's a thing you need to keep in mind when you're doing a reinforcement learning algorithm. You want to make sure that it actually understands the difference between exploration and exploitation, and you should have some kind of a discount factor. Like we can have something like a gamma factor, wherein you're not giving reward to everything. Like for example, if it gets a cheese, you should not just give a positive reward, but if it goes again and again, you can give a discount factor. Like again, if it comes over here, I'll give a maybe like 50% less, but if it goes over here, then you will get a more reward. So that's something you need to decide based on each game. Some of the games might have like a different factor of exploration, wherein you want to make sure that you explore everywhere before going into one place, or you want to just exploit the nearby resources. Maybe you're playing a game wherein you just want to maximize the nearby points rather than going into like far by places and exploring all the things before considering like which one to choose. So that's something we can consider. Some other factors that we need to consider for learning agent. So these are like 4 important things like we should consider while you are having a reinforcement learning agent. There is a learning element. Learning element is the new skill that can be learned to make sure that agent is being improved. So what step can be done, like maybe like moving one forward or moving one step backward, or what kind of skill that can be learned by the agent. That's called learning element, and there's something called performance element. Basically, the system is able to generate some input and take some decisions based on that input. The performance element is something like that you make sure that you use the correct input, and you try to make sure that you actually take some decision based on the input. Like you use the previous state and you use it to transition into the next state. And problem generator. So it's really important to have some problem generator, because element it's kind of an element which generates a curiosity. So instead of like the classic example of rat and cheese, you don't want the rat to just explore the nearby places. It needs to have some curiosity and some problems for the agents to navigate. It should not be like exploiting only the nearby resources, but going into the farther places as well. So problem generator is also an important factor to consider. And the critic. Critic is basically the performance analyzer. So at the end of the day, you want the agent to win the game. So one big critic could be the whether it's able to win the game, and then that could be a performance analyzer, or it could be like maybe it just made it to the next level. For example, in Mario game, you want to make sure that it goes at least to the next level. So that could be a critic, or it could be a performance analyzer. So these are some factors that you need to consider while considering a reinforcement learning agent. And reinforcement learning agent is not just for games. It can be applied to numerous applications. Like you can see, like games is just one subset. Like there are so many games that wherein you have reinforcement learning agent, like not just board games, but you also have the games like StarCraft, which is really complex. And you can also play. You can also use a reinforcement learning agent to play on for robotics. So wherein you can have like a simulation. So you can have the robot to move around in the simulation, and from the simulation you can actually transfer it to the real world. So that's something will be going on later. And you can also apply to other deep learning fields like computer vision, NLP, and so on. So the applications of reinforcement learning is wide. So it's just not for games, but games actually gives a test bed, because you can actually test all the agents in the game, and once you have the agent working in the game, you can actually transfer it to real world. So let's learn, like take the example of robotics. So the goal of robot, like let's take this particular Boston robot. So Boston robot like by MIT is really famous. You must have seen a lot of videos of it doing flip backs and all those like jumping those hurdles and things like that. So the goal of this robot learning, like let's say, is to use machine learning in general environments. So one big problem of robots is they do not generalize well. So actually robots, they can do a lot of things. Like you can program them by some rule-based approaches, and you can have some kind of a controlled environment, as you might have seen those MIT Boston videos, where they have like a real test bed, where they have like a lot of hurdles and it kind of jumps from those places. But it really has a big trouble when it comes to general environment. For example, if I go and kick this robot, it may not be programmed well, or it may not know like, okay, if I kick it, then it has to stand back. So those things might not be programmed well, but machine learning can really help with that generalization problem. So let's learn how. Let's take this example of robot grasping. So this is a problem wherein you have a robot arm. As you can see in this example, this is a arm, just one arm, and you have like a single viewpoint. You have let's say you have a top viewpoint wherein you have a RGB camera, a colorful picture, and basically you command this arm to grasp objects from this bin. So you can see there are some items in the bin, and you want to make sure that it picks that particular item. So only thing that robot knows is a picture. So it knows that there are some items through that particular top view, and the model must learn the hand-eye coordination. Like it should know, like, okay, when I go down and then I have to pick it up. So that kind of motion, which might sound very trivial for humans, like, okay, I just have to pick this. What are you saying? Like, just pick it like that. But when it comes to a machine learning model, basically it just gets an image of it. It doesn't know anything else. So with that information, how do we go about it? So that's something we'll be learning. And there's something called the sim to real transfer. So you can look into this paper for more details. But let's say like you have this particular robot. So how do we go about it? So one approach would be like, okay, I'm going to make sure that this robot trains like maybe like 10 days or 20 days. And I'm just saying like, okay, you pick this object, and you might fail. Okay, if you fail it, I'm going to give a negative reward. You keep doing it. So at the end, I may not get the results, right? So at the end, even after 10 days, I may not get like good results which I want, because I'm just giving it like one image which has that object. I'm telling, okay, just go and pick it up. So that's really not going to work. Okay, so what we can do now? Okay, let's take an arm farm. So let's take that we have like a lot of arms. Like let's say that you've got really good research funding, and you've got like six arms, and you got like six robots, and you use some data like collection. You collect like 1 million attempts of grasping those objects. You collect lot of data from it. Like you probably, like you're saying, like, okay, let's train some supervised approach. I'm going to collect a lot of data, and using that, like let's say you collected 1 million attempted drafts over like thousands of hours. So you just keep telling the robot like keep doing it for like entire 10 days. It might be like very fast than one robot. Obviously it's going to take lesser time compared to one robot, but it still will take a lot of time. So it's not really ideal to have like maybe like 10,000 robots or something. One thing might be like funding might not be there, and you don't have that many objects as well to pick up. But you can one thing you can do is you can have a simulation. So let's say you have the same thing. So you're just simulating the exact environment which you have in real world. You can reproduce using the graphics, right? You can. There are so many agents like Unity ML, which I'll be talking about later, wherein you can make this particular environment. So you can make the exact environment which the robot will be dealing with in real world, and you can reproduce this setup in simulation. And simulated robots are very easy to scale. Like you can have like a cloud instance, and you can have like maybe like millions of robots training, right? So you can have like a lot of simulation, and you can have like, let's say you have thousands of simulated robots, and all those are like some, and all the objects also randomly generated. You can have like n number of objects being generated, and it can be done like multiple times. So you can easily get a lot of data which you want, and you don't have to worry about like, okay, how long it's going to take and things like that, because it can do like a lot of graphs, millions of graphs, in just hours, instead of like taking weeks in case of like having an arm farm and things like that. So you can definitely check out this paper called sim to real transfer, when, as I mentioned right now, like we can take a simulation, and we can transfer those techniques which we learned in the simulation into real world agent. So whatever this reinforcement learning agent is learning through this particular simulation, it can actually be transferred to real life. Obviously, there are some more changes that I'm not mentioning right now, which is might be out of scope, but we can actually do this process. This is something that I would say is a game changer, because when we can train agents and bots like this into a game environment, and then transfer it to real life, we don't have to worry about the costs, and we don't have to worry about like, okay, if it fails, I'll be losing. Suppose you have a really expensive robot which you have built for like say $1 million and things like that. You don't want that particular robot to like fail, and then it stops working and things like that. But if you have a simulation, you can actually test it out, and it's more easier to transfer it to real life. So there's some tools like OpenAI Gym tools. So OpenAI Gym tool is like a toolkit where you can develop and compare all the reinforcement learning algorithms. So all the like algorithms are available over there, and it's like really, they have really good documentation as well, and it supports like teaching agents, and they also have like really cool gaming environments, as you can see over here. So they have like a lot of agents which use reinforcement learning, and also they have some kind of environment where you can test them. So apart from that, they also have like a support for like a third party environment. Suppose you say like you want to play a Fortnite game, or maybe like you want to play some simple game like Temple Run or Subway Surfers. You can actually simulate a agent using the environment. You can that can be controlled on through OpenAI Gym. So this OpenAI Gym, like it's really useful for like testing and developing those reinforcement learning algorithms. So definitely check this tool out. And apart, let's take a small demo of like an agent that's been created by OpenAI. So in this case, they have a multi-agent setup. So they have like a blue agent and a red agent. And in this case, the blue agent is trying to hide from the red agent. And you can see this particular demo, like what they have done. Uh, So as we can see, so as we can see over here, like this is like a environment that's been which has been created by OpenAI Gym. So what they have done is they have created a simulation wherein the agents can go around and play hide and seek with each other, and so the goal over here is like the blue agents will be playing against the red agents. So the red agents are trying to like find the blue agent, and the blue agent is trying to hide from the red agent. And after like training like millions of iterations, they found that okay, like if I place some blocks over here, then I can actually hide from the particular red agent. So the red agent cannot like move the blocks, and they are able to be safe from the red agent. And even if you have like multiple doors, they're also able to lock all those doors, and they're able to make sure that the red agent is not able to reach their location. And the thing about here is like both blue agent and the red agent both are trained using a reinforcement learning agent. So the algorithm they use is like to maximize the reward. So the reward for a blue agent would be to maximize its reward. That is, the red agent is not able to find it, and the goal for red agent is to maximize its reward, which is to make sure that it's able to find the blue agent. So in this case, like when the blue agents are blocking the doors so that the red agents are not able to reach, let's say like you have this ramp when the red agents can actually climb the ramp and can jump into this particular environment, then the red agents are able to even learn that okay, let's take this ramp and actually go and jump into this. That's what the red we can see over here. But after millions of iterations again, like what happens is like previously the red agents were smart because they were able to get onto this ramp, and they went inside the like this particular room. Then the blue agents understood that okay, so this ramp is the one which is causing all the issues, so let's keep the ramp inside. And they actually are able to learn that okay, let's keep the ramp inside and let's lock the doors. So that's what they have learned, as you can see over here. And the good thing over here is you don't have to like mention like okay, so if you block this block or something, we'll give you a positive reward or something. So the agent actually learns by itself to understand like okay, this is what it has to maximize, and this is what will help it to win the game. So the good thing about this is like you don't have to like train just one iteration. So you can have like millions of iterations, and over millions of iterations, you'll understand like which is the best way to win this particular game. So and they also tried with like having open door games or something like that, and even with that the agent is able to understand like okay, if I lock myself in this particular orientation, then the red agent won't be able to find. And this is a really interesting video which you can watch. It's really cool way of like training agents. But the most interesting thing is like you don't have to have this one environment. So the millions of iterations which I was talking about was just for this particular agents when you have two red agent and two blue agent. But you can have like millions of red and blue. So that will be like a million times millions. You can have like so many iterations wherein you just don't just have like a particular reward function from this particular environment, but you can have like a thousands of those environments, and from all those environments you can actually learn, and you can observe like what's happening. You can have like a probably like a millions of agents learning from the million experience from all these agents. So this is a really cool concept that there's like done by OpenAI. So they have like a lot of such environments wherein you can explore, and This is a really trending research topic which is going on. You should definitely explore it. And there's also some tool called Unity ML tools. So Unity ML actually provides an environment where you can create those game environments. So OpenAI basically just helps you to train all these reinforcement learning agents, and they have some preset environments. But Unity ML actually helps to they have like Unity 3D tools wherein you can actually build an environment using Unity, and you can use some simple Python API. Basically, they have an open source project. So if you're interested in pursuing more research on machine learning for games, then I will highly suggest using Unity ML, because you can actually create your own game where you can have like a small game simulation, and then you can serve it as an environment, and you can train your own like reinforcement learning agents with that, and you can have multiple agents as well. As I mentioned, you can have like say if you have two agents which have the same brain, that means they use the same algorithm. So it's really easy to do research, and you can have like one agent which just is a rule-based agent, and you can have like a different age algorithms running parallelly on different agents. So on the same learning environment, you can have multiple agents that are being training, and you can use Python, which makes it really open source, and you can easily configure with all your machine learning projects. And these are some other resources to get started. I would highly recommend Andrew Ng's like deep learning course before getting started into reinforcement learning. And also you can try courses like fast.ai, where they have like really hands-on application based course. And you can also like go explore into all these tools, especially Unity ML and OpenAI Gym. And these are some resources that get started. I'll put the link to the all these slides at the end. And that's it for the presentation. Thank you. Um, if you have any questions, we can dwell into that. Yeah. Also, feel free to connect me on LinkedIn if you have any questions. I'll be happy to answer.
Thank you, Abhilash, for such a wonderful talk given by you. And I think this will bring the interest among our students, and they will start doing some good projects in machine learning, and they'll develop their research work in machine learning. I think so. I hope our students will contact you for further ideas. Thanks for your consent to accept this event and given a wonderful talk. Once again, I'm thanking you to join with us, and also looking forward to collaborate with you in near future. Thank you, Abhilash. Thank you. Thank you, one and all.
Thank you for this opportunity. Like, if is there any question, then we can answer that. But yeah.
Thank you.